Okay, welcome back to Warmstarting via meta-learning across tasks. Today we will discuss the setting what happens if we have multiple tasks, which means if we're solving hyperparameter optimization on the sequence of tasks, how can we leverage this information for solving a new task? This is a very typical setting because we often retrain models to track changes in data streams, or we train models on multiple related and similar tasks. And the idea is that the best setting tends to remain stable across similar tasks. So again, we want to boost the efficiency of hyperparameter optimization via transferring knowledge. A motivating example is I have here is this illustration of runtime and error in blue and green. Lower is better for two different hyperparameters on three different data sets. You can see that the model size, for example, the runtime on all three data sets increases with the model size. Not really surprising. On the other hand, the learning rate, here the blue curves on the left column, they behave very differently, whereas on the first data set, you want the optimal learning rate is different from the two other data sets. The question is now, if we have a data set D, how can we leverage the information that we have gained from solving these tasks for our new data set? So more formally, again, we assume that our search space stays fixed. So we have a single machine learning pipeline with a fixed search space. A given target task or target data set, DT, and new here we do have a set of metadata sets, dmeta, of size t-1, on which we have collected prior observations because, for example, we have run hyperparameter optimization on them before. Why do we think this is a good idea to use that? Because we hope that objective functions of the tasks are somehow correlated, which allows us to do positive transfer from similar tasks and ideally also zero transfer from different tasks. The method that we're going to use is portfolios. So we want to find a set of configurations that we can use to partially replace the initial design. Now, the main question is, how do we get this portfolio? How do we build this portfolio if we have our metadatabase? There are two options. One is we build a task-agnostic portfolio offline once that covers well-performing regions across all tasks. So this covers very diverse settings. And option two is we build a task-specific portfolio for our target data set, which covers well-performing regions on similar tasks. So let's have a look how we build such portfolios. For the first option, we assume that for our metadata sets, we do have a candidate pool of configurations, which is typically the best configurations that we have observed on these data sets. And the goal is then to construct a portfolio, so a set of configurations. In this case, we want to find K configurations, so we want to build a portfolio of size K that minimizes the objective. And our objective is we sum for all data sets, we find the configuration in our portfolio that performs best, and we sum that over all tasks. Intuitively, this means a portfolio that minimizes this loss function will cover optima across diverse tasks, and it will also ideally include at least one well-performing configuration per setting. And this means its performance is defined by the single best configuration per task. So it's not the average performance per task, it's the best, the minimal cost per task. And a straightforward way to implement this is by running greedy forward selection. So we greedily, in each step, add a configuration that improves the performance of our portfolio on uncovered tasks. This encourages diversity via complementary performance. So in pseudocode, this means as an input, we get candidate configurations on our metadata sets and the cost function. We initialize our portfolio empty, and then we run case steps. In each step, we identify the configuration that minimizes the loss function from the slide before for our portfolio. If we would add this configuration, once we have found this configuration, we add this to our portfolio, we remove it from the candidate set, and we iterate till we have found such configuration. As an illustration here, we have here a performance matrix of 5 configurations. So we have 5 candidate configurations, and then we have data sets on the x-axis. The colors correspond to the performance of these configurations. Yellow means configurations perform very good, and darker color means they perform very bad. If we would run our pseudocode, the first configuration that we would add is this configuration, because on average it performs quite well. It's the configuration that performs best on average. It's not really the best of any of these data sets, but it's also not the worst. In the second iteration, we would add this configuration here, because it performs really well on these 3 data sets. It does not perform that well here, but this doesn't matter because we already got these covered by our first configuration. So this one complements the first configuration. In the third step, we would add this configuration because it complements the previous 2 configurations on these 2 data sets. And then we would iterate on and iteratively add the configuration that improves the portfolio performance. So now going to the other option, building task-specific portfolios. So right before we built this offline in this costly procedure, one portfolio that we would apply for all new tasks. Here we want to build one portfolio for each new task. So instead of finding this global portfolio, we want to build it dynamically, specifically for a task. The key idea here is that we adapt our greedy portfolio construction by reducing our metadata sets to contain only the k closest or most similar tasks, and then simply use the best performing configuration on these tasks to start optimization. So the key question here is, how do we define task similarity? So when we have our new task, how do we find the k closest data set in our metabase? And why is this important? Because if we can measure data similarity or task similarity, and we assume that similar configurations assume similar performance, we can transfer the good performing configurations. And the most simple, so the most common way to do that is to do this similarity via meta features. Meta features are dataset descriptors that are defined as functions that you can run on the dataset that will give you a value which represents a dataset characteristic. Very simple meta features are, for example, the number of samples and the number of features, or the number of missing values, and so on. But there are other types of meta features. Others are information theoretic meta features, for example, entropy of features or labels. In general, you can describe the distributions of feature values. And another category are model-based features. For example, if you train a very simple machine learning model on your task, for example, in this case here, a decision tree, and then you take the depth of the tree or the number of leaves, or you directly use the performance. Once you have decided on a set of meta features to use, you can compute task similarity as the distance between these 2 vectors. So based on this, we can now also write down our updated portfolio building. We compute our meta feature vectors C for all data sets, including our target data set. We compute the k closest data sets, and we use the best performing configurations of the data set as the portfolio. So now I show you 2 ways to build portfolios. Let me contrast them. For the task-agnostic portfolio, as I said before, this can be built offline once. It covers diverse settings, and ideally also the setting that is in DT, our target task, and it emphasizes complementarity in configurations. In contrast, the task-dependent portfolio is built per task, so this is really specialized. And it requires hand-designed meta features or another way to compute task similarity, and it emphasizes performance because you want to find the best performing configurations on a new task, which might result in configurations that are very similar. Of course, there are also some alternatives and extensions to this. Instead of meta features, we can also use ranking-based similarity. We are directly comparing performance across shared configurations of tasks. So if you have 3 algorithms, ABC, you run them on your task, you can compare on your data sets, you can compare the ranking. Secondly, we can also learn the similarity via task embeddings. Dataset to VEC, for example, is a very prominent example, but of course we could also just use embedding of textual descriptions. Lastly, we could also, instead of portfolio, we can also directly combine our ensemble surrogate models that we built on our previous tasks or on our meta tasks, or we can combine an ensemble acquisition values. So lastly, the conclusion and key takeaway from this video is prior observations on related tasks can increase the efficiency of Bayesian optimization. We talked about Warmstarting via task agnostic and task-specific portfolios. And we also talked about how task similarity can be defined using meta features or configuration rankings or even learned embeddings. And as usually, if the assumed task similarity is incorrect, and this only applies for the task-specific portfolios, transfer can be harmful because then we might have negative transfer.